In this video, I will continue with the next unit of this chapter, which is related to energy. Now, you already have studied different types of energy. In nature, energy exists in different forms, but we will mainly focus on mechanical energy and its types, which are kinetic energy and potential energy. As per the definition of potential energy, it is the energy possessed by a body by virtue of its changed position or changed configuration. And hence, there are two kinds of potential energy: gravitational potential energy and elastic potential energy. Gravitational potential energy is due to changed position of the object, while elastic potential energy is due to the changed configuration of the object. Next is kinetic energy. Kinetic energy is defined as the energy possessed by a body by virtue of its state of motion. A body can have three types of motion, and hence there are three types of kinetic energies. If a body is moving along a straight path, that means the motion which it has is translatory motion, and therefore the energy possessed by the body is translational kinetic energy. For example, if a body is falling freely, then the motion it is having is translational motion, and the energy which it is possessing is translational kinetic energy. Rotational kinetic energy is possessed by a rotating body, for example, a spinning top. And vibrational kinetic energy is possessed by a body having vibrational motion. For example, the molecules vibrate about their mean position, so they possess vibrational motion and hence vibrational kinetic energy. When you fix a wire or you clamp the wire at both the ends and you struck the wire in the middle, it will vibrate, so it will possess vibrational kinetic energy. In this chapter, we will mainly focus upon translational kinetic energy. Since kinetic energy of a body or an object is the energy that it possesses due to its motion, and therefore the formula for kinetic energy is given by half mv square, where m is the mass of the body and v is the velocity. Kinetic energy is directly proportional to m, which means that the more the mass, the more is the kinetic energy. In simple terms, if you double the mass of a body, the kinetic energy will also be doubled. The second factor on which kinetic energy depends upon is velocity. Kinetic energy is directly proportional to velocity square. If you double the velocity, then kinetic energy will become 4 times. And hence, velocity has greater effect on kinetic energy as compared to mass. The SI unit of energy is joule and hence is the unit of kinetic energy. So, it also has the same unit as that of any other energy form. Next, in this slide, we will study about the relationship between kinetic energy and momentum. Definitely, there is a relation between these two, as both of them are properties which are linked with mass and velocity. Kinetic energy is given by the formula half m V square, while potential energy is given by the formula mv. So, in both the expressions for kinetic energy and momentum, they contain mass and velocity, and hence kinetic energy and momentum bear this relationship, which clearly shows that if for a body, moving body, if the momentum is constant, then kinetic energy and mass are inversely proportional to each other. Hence, we can say that for momentum constant, kinetic energy is inversely proportional to mass. So, if there are two bodies with same momentum, then we can write the relationship between kinetic energy and mass as this. The ratio of the kinetic energies of the two bodies is equal to the ratio of their mass, but since E and M are inversely proportional, hence the expression goes in this way. On the other hand, if I assume that for a body the kinetic energy is constant, then momentum is directly proportional to root m, and hence can be given as momentum of two bodies will be expressed in this way. There is a third possibility also, children, and if now we assume in this expression that mass is constant, for a body which is in motion, if the mass is constant, then momentum and kinetic energy are directly proportional to each other, and therefore mathematically they can be written as in this way. So these are the three relationships that exist, not relationship but the ratio that exists between momentum, kinetic energy and mass. Out of the three, one is constant and the rest of the two are related in the manner which was shown just now. Now, there is a theorem known as work energy theorem. When force is applied in the direction of motion of a body, it accelerates the motion, which increases the kinetic energy of the body. And this increase in kinetic energy is actually work done by the body, and the expression for the work done then is given in this way, where W is equal to change in kinetic energy, which is equal to half m Vf square, where Vf is the final velocity and Vi is the initial velocity. So let's see how do we obtain this. If we consider a body of mass m moving with some velocity Vi and is under the application of certain force, then if we assume the force to be constant, then work is given by F into S. From equations of motion, we know very well, or we can find out the distance travelled by the body, which will be equal to distance travelled will be this. This would be the expression for the distance travelled by the body. Also, from Newton's law, F equals to ma. So, on putting the value F equals to ma in this expression as well as the value of S over here, we will get W equals to half m v F square minus half m v I square, which is nothing but change in kinetic energy. So basically, work is equal to change in kinetic energy, and this is the work energy theorem. Now next is potential energy. Potential energy has two forms: gravitational potential energy and elastic potential energy. In this particular chapter, we have concentrated only on gravitational potential energy. In the first figure, where the man is hanging with a rope, you can see different positions of this person. Gravitational potential of an object is directly proportional to its height above the zero position. As mentioned in the previous slide, that gravitational potential energy is given by this equation, which is mgh, where m is the mass of the body, g is the acceleration due to gravity, and h is the height. In the first pic, you have seen very well clearly that this is the position, or at this position the man has maximum potential energy because it is at the maximum height. On the other hand, at this position the person will have minimum potential energy because it has, as compared to three states, it has minimum height. That means it is at minimum height above the ground level. Then there is another picture which is showing the value of potential energy at the maximum height, which is 50 joules. If I assume acceleration due to gravity of this place be 10 meter per second square, then potential energy at point A will be 40 joules. Potential energy at point B will be 30 joules. Potential energy at point C will be 20 joules. At D it will be 10 joules, and finally at the ground level it will be 0 joules. That means as the height decreases above the reference point, the potential energy decreases. Or we can say that as the height above the reference level increases, the potential energy increases. There is one more picture in which the man is lifting some load of weight 10 Newton up to a height of 2 meter. So, if I ask you that calculate the work done by the body, then what will you do? You will definitely find the potential energy in lifting the body from ground level to the height of 2 meter. So, as per this, 10 into 2, the potential energy will be 20 joule, and this is the amount of work done by the body. So we can say that work done is also equal to the potential energy spent by the body in lifting the object. There is one more picture, and in the second picture there are various points mentioned or various positions mentioned. Number 5 is at the maximum height, so potential energy at 5 is maximum, and number 3 is at the minimum height, so the potential energy is lowest. But the question arises, when height decreases, potential energy is decreasing, so where is the remaining energy going? Is it lost? Then the answer is no. The energy is not lost. Energy is always conserved as per the law of conservation of energy. According to this law, Energy can neither be created nor can be destroyed. It can only be transformed from one form to another, and the total energy of the system will remain constant. That means when the height is decreasing, potential energy is surely decreasing, but it is not lost. However, it is converted to some other form, and we will understand with the help of the example of a freely falling body. At the maximum height, as you can see in the diagram, there is a ball and it is at a height h above the ground as shown in the figure. The ball is at rest, so its initial velocity is 0. So if I ask you calculate the potential energy at point A, then according to the formula, if the body has mass m, then potential energy will be mgh. And since the body is at rest, so kinetic energy is 0, which means that total energy is equal to sum of potential energy and kinetic energy, which will be mgh. This is the potential energy at point A. Now let's see what will be its position after it has travelled a distance x. From the top it is falling freely. This is the direction of motion as shown over here, which is downwards. So now after travelling a distance x, it has reached the point B, and let's see what is the total energy now. At point B, if I want to find out potential energy, the formula says mass into acceleration due to gravity multiplied by height above the ground level, and it is at the height of h minus x above the ground level. In order to find out the kinetic energy, which is given by the formula half mv square, now kinetic energy is not 0. So we will have to find out the value of kinetic energy. So applying equations of motion, v square equals to u square plus 2gh, where h stands for the distance travelled, which will be, in this particular situation, it will be x. It has travelled a distance x. This is the distance travelled. U is 0 as per the given conditions. So v square is equal to 2gx. On putting the value here, we will get kinetic energy as mgh. mgx. This is the value of kinetic energy. So, the total energy at point B will be equal to mgh minus x, which is the potential energy, plus mgx. On adding both of them, you will get the value of potential energy as mgh. So the same value you have obtained at position A and the same value you have got at position B. Let's find out what happens at C. At position C, the value of potential energy will be 0 because h is equal to 0. It is at the ground level. But again, on finding out the kinetic energy by using equation of motion, we will find that kinetic energy has come out to be mgh now because it has travelled the entire distance. The distance from point A to point C is h, so hence kinetic energy is mgh, and therefore total energy at point C will again come out to be mgh. And hence we can say that 1 energy is converted into another energy. Same scenario is observed for a simple pendulum. And you can see in the diagram that at the base, that means at the reference level when height is 0, the potential energy will be 0 at the center position. But at the maximum height from the reference level, the potential energy will be maximum, which will be equal to mgh. But kinetic energy will be 0 over here. Kinetic energy will be 0 at the extreme position and potential energy will be maximum. And the same is depicted here in this graph. When height increases, the kinetic energy decreases, it falls. But potential energy increases. But at all points, the sum total of kinetic energy and potential energy remains the same, which is equal to mgh. At the midpoint where both of them are intersecting, this is the distance h by 2 or height h by 2. The value of total energy is mgh, but potential energy and kinetic energy are equal over here, which is mgh by 2. So this graph represents the variation of kinetic energy and potential energy with height above the ground. So there are many energy conversions that we observe. I have mentioned only a few of them. For example, when water falls from dam, the potential energy at that height is converted into kinetic energy of falling water, which is then used to rotate the turbine of a generator to produce electricity. Similarly, when you are when there is some vehicle moving, then the chemical energy of the burning fuel is converted into kinetic energy. If you have a spring and it is compressed, it has elastic potential energy due to its deformed shape. And when it is released, it is converted into kinetic energy. So you will find many similar examples related to energy conversions in your day-to-day life.